So now let's talk about determining the short-run behavior of polynomial functions. So some pieces that describe the short-run behavior, we can talk about the zeros of the graph, which the zeros of a polynomial is the same thing as the x-intercepts. So we can find those. We can, something we're going to do here is relate the degree of the polynomial with the number of zeros we'd see. Also, another piece will be turning points. So turning points like these green points on the graph here. So in pink, those are the zeros of the graph, and in green, those would be turning points as we turn direction. That turning would be from increasing to decreasing, decreasing to increasing. So in fact, these turning points, those are going to relate to our local minimum and maximum values. And another piece that we can use that will really come up in a future video, but another piece would be our y-intercept, would be part of our short-run behavior. So in this video, we're just going to focus on zeros and turning points, and in fact, zeros will go into more depth in the next video. But in general, let's get an idea of those two pieces. So for these examples, what we're going to do for each polynomial is determine the degree, find the number of turning points, find the number of zeros. And then with that, we want to look for kind of a theme between those three values. So with this first case, if I want the degree, so the degree I can get from just the general shape of this graph. This very much looks like a parabola. So I could say even degree, but I'm going to go with degree 2 because this has a very clear shape of a parabola. So this is degree 2. Now the number of zeros, we can see with the pink dots, this is a case where there are 2 zeros. And number of turning points, we have this one and only turning point. So with this graph, we can see it's degree 2, it has those 2 zeros, it has 1 turning point. Let's go to our next graph. This graph here, for the degree, this is going to be degree 3. This is going to be the shape of our cubic function, just has a few more twists and turns to it than our standard one that goes like that. But we have this coming from negative infinity and then eventually goes off to positive infinity. We just have the short run behavior that's occurring in here. We can see that there are 3 zeros. We can see that there are 2 turning points. And the zeros are where we're intersecting the x-axis. Turning points is where we're switching from increasing to decreasing, or you can think of it as those local minimum and maximum values. All right, figure 9 here for the degree. And this can be a bit tricky, so I'm just going to tell you, this is degree 4. What we can see, it's an even degree because of the end behavior, that long run behavior of our graph. We're going off to positive infinity on either side. And then knowing that it's specifically degree 4 is actually coming through with how many twists and turns we have and x-intercepts and all that. But let me just tell you, it's degree 4. And then from there we can see we have 4 zeros and we have 3 turning points. All right, then our last piece here is from the long run behavior. I can see this is odd because we're coming from negative infinity and then going off to positive infinity. So I know it's an odd degree, and then I'll just go ahead and tell you that this is degree 5. Kind of going with the theme of our other degrees. Number of zeros, we can see we cross that x-axis 5 times. And with this graph, there are 4 turning points. All right, so with this, what we're trying to get at is a theme for how these zeros and turning points are behaving for an nth degree polynomial. So given the degree of a polynomial, and I'm not just going to say the number of zeros, we're going to say the maximum number of zeros. So with our 4 cases here, if we compare the degree with the number of zeros, we see that it matches. So our degree matches the number of zeros, and this is really the max number of zeros. So our maximum number of zeros is just going to equal the degree of our polynomial, which is n. Now, why we're saying maximum is because we could have less, especially if we think in terms of our polynomial, or sorry, our quadratic here. Let me get a different color, because this could have looked like this. And that would be a case where we would only have 1 zero. And that's completely fine. It's still degree 2, it still has 1 turning point. We even could have had this case where there are no zeros. Still has 1 turning point, but it would be a case of 0 zeros. So with that, this is giving our maximum would be 2. There's no way we could end up with 3 zeros in this case. We couldn't have a third one, because then our graph would have to turn and cross, and then it would become an odd degree polynomial. So it would all fall apart. Then we'd even have more turning points. So with this maximum number of zeros. With the number of turning points, it's going to be the same idea. We're going to say that this is the maximum number of turning points because there could be less. So just keep in mind that this is just a maximum value. So comparing our degree with the number of turning points, so degree 2, 1 turning point, degree 3, 2 turning points, degree 4, 3, degree 5, 4, it's 1 less. And these graphs are specifically drawn in a way that are showing this maximum number of turning points, so we couldn't add on any more, because then it would mess with the degree of the polynomial if we switched it around. Kind of like I was saying over here, I couldn't have another 0 because then we'd be adding another turning point, and then it would become an odd degree. So this sets the maximum number of turning points, and what we do is we take the degree of our polynomial minus 1. So that's some behaviors of our polynomials and their short run behavior, looking at these turning points and zeros. What we're going to do in this next video is really focus on the zeros of our graph, because that really sets the pieces for our short run behavior.